Okay, it's my pleasure today to introduce Tong Zhang, who is a professor of statistics at Rutgers in New Jersey. And before that, he was at Yahoo for a couple of years. And before that, he was at IBM for like 7 years, I think. And before that, he did his PhD at Stanford very fast. And before that, he did in computer science. And before that, he was at Cornell, where he did his undergraduate degree in math and computer science. Is that right?
Yeah.
Great. And he works on machine learning, and therefore on the mathematical side of NLP. I've followed a number of his papers over the years, and they've always been extremely interesting and well written. And I'm looking forward to a talk which is extremely interesting and well spoken. So let's give a hand to our presenter.
Thanks for the introduction. So it's actually a very pleasure for me to come here. I heard of this place. There's when I was at IBM, which one I was more involved with NLP. Of course, there are people going to both directions, and from IBM to here and here to IBM. So it's really great for me to finally come to see all the people and the famous people also here. So we will talk about the topic is not quite NLP here. But hopefully it's related. So it's more about machine learning than natural language. Basically, what we want to do is doing sparsity, induce sparsity in machine learning. There are basically two issues I want to talk about in the sparse learning. So mainly it's focused on the computational issues. One problem in the computational issue is scalability, which is actually part of work I have done at Yahoo. One thing we're interested in is to look at some algorithm which can handle large-scale data. And one way to do that is by online learning. The reason online learning will be useful for large-scale data is because it doesn't need to store all data in memory. Then online learning doesn't really do sparsity, and we'll probably say a little bit further. And then this talk is about how do you achieve sparsity in online learning, and I will say why you do that. The second topic is again on the computational side, which is to say that in a lot of machine learning problems, you can have very difficult algorithms. For example, NP-hard problems, which is really the formulation you want to solve. But then you cannot solve NP-hard problem. We don't know how to do that, so we want to use some relaxation method. A lot of people focus on convex relaxation or some other approximation method. I'm not talking about convex relaxation in this talk, but I want to look at some approximation method and the effectiveness of that. Example I will give in this particular is again in the sparsity setting, means feature selection problem, as well as sparse learning in the batch setting. So one is online setting, which is about scalability. How do you do sparse in the online setting? Another thing is in the batch setting. How do you do sparse learning in the not necessarily scalable, but at least it can do a good job of provably good performance. And in particular, I'll talk about greedy algorithms and their effectiveness.
So did you say provably good performance?
Yeah, provably good performance. That's actually what I'm more on the theoretical side, algorithm side. So one thing I'm interested in looking at algorithms which actually have performance guarantees, and we will see that in both talks. We'll look at the performance theoretical issues. So here is part one. Essentially, the motivation is machine learning over large-scale data. For the particular example, there are actually larger examples. But for the particular example we look at is a click prediction problem at Yahoo. Then there is basically, this is typical NLP size. In fact, you can have larger data. In particular, for example, in the click prediction, you look at ads and you look at the page which you try to match the words to words to say how good one word match to another word will be the best combination. In that case, you really have, let's say you have 10 to the 8th is the number of words you have, then the total combination will be 10 to the 16th. It's just the square of that. You have large-scale data, large-scale features, and you have also depending on how do you count training examples, it can be larger than this, but that's this particular data set we will look at that time. At the time I was there. So the online algorithm is suitable for this kind of a large-scale data simply because it does not need to store, as I said, it does not need to store data in memory. So, okay.
Just to give you, I mean, you gave me some idea by talking about words, but
right.
How many features might fire at on any one example?
That usually is smaller, much smaller. So maybe 100 or that's typically it's sparse. Yeah.
Yeah, that's your point below. When you say the online algorithm, you mean perceptron?
Perception type or perception is online. Yes, basically you look at one data at a time.
Yep.
You don't load every data into your memory, but just look at it and you cycle through the data. So that's an online algorithm I'm trying to look at. Even you just huh?
Here's example.
Oh, okay. Go ahead.
What do you mean by store all the data in memory? Do you mean the model or the training data?
All the training data. So,
I mean, which method needs that?
batch size, any batch method will need that. For example, if you want to use conjugated gradient to solve logistic regression, you will be able to. You have to load everything in memory. You cannot run just look at one example at a time.
Well, memory is like RAM, but you
It's
have
RAM.
access to all the data at the same time for batch update.
Okay.
When I talk about actually, I'm saying RAM. So,
He says here you can, if you have streaming data, then you can throw it away as you get it. So
right. This is more like streaming data.
pass over the data.
So online learning is more like dealing with streaming data. There is one issue here, is which is a motivation of this research, is that traditional online algorithm doesn't produce sparse weights. For example, perceptron. And why you want sparse weights? Space constraints, for example, it can overflow RAM. If you say you have, let's say, 10 to the 9, maybe 19s instead of 9s, then you want to, every time you go through the data, you want to make sure you always maintain a sparse number of weights instead of all the weights. You can do it heuristically, and here I want to have a more principled solution. Test time constraint is if you have a more dense model, it could mean more test time. But there are other issues why you want sparsity. Basically, this is the main consideration we have. Our goal is doing sparse online learning, which essentially say learned weights will be sparse in your online algorithm. And this is has interest. I talked to many people, at least recently. This is just recently. Some people start to be interested, but so far hasn't been proposed algorithms. And this particular, what we done is really the first of such algorithm, which can do that in the online fashion. So online sparse learning. And we will show how to do that. Questions, or I should go on?
Yeah, just curious about your comment that it was the first such algorithm.
Yeah.
So there's an algorithm called Mira that you probably know.
Actually, I don't know. What is that?
Okay. It was done by Kobe Kramer and colleagues
Okay.
when he was a postdoc at UPenn.
Yeah.
So the idea is that it's sort of like perceptron,
Right.
except that the updates are sparse. For every example, it solves a small quadratic program.
Right. Those are a little bit. I don't think it's the same. I actually talked with Kobe Kramer.
Small but not sparse.
Yeah.
Yes, but you could do it with L1 instead of L2 regularization, and then it would end.
No, it's not. It's not. That's what I actually want to talk about.
Exponentiated gradient descent.
Right. It's not quite. And talk to him. He's actually interested in subject, but I don't think he has anything really producing. He's one of the person who is interested in this online learning, and I actually talked to him. So he is interested in this thing. But no, I don't believe they have some principled way. I mean, always curious. I would say a little bit some naive approach, simple approach. It could, I guess maybe he's addressing a different aspect, not exactly inducing the.
Let's hear your.
Okay. So yeah, this actually is simple, our method, but we will say basically this is setup, online learning. What does that mean, right? So it's sequential data, streaming data. You have X is input, Y is output. That's typical machine learning setup. You have Z is, I just say, the input output. And the weight vector is what you want. It's essentially, we have a linear prediction. This weight times inner product of weights and your input is your prediction output. And the loss function, for example, least squares is that, but you can use other loss function, maximum entropy, SVM, whatever. But essentially, loss function depends on your weight vector, becomes your data, and this is linear prediction, and the difference of that with output. So that's kind of, essentially in the online learning, what's one thing people interested in is aggregate loss. Means that when I make a prediction, I will do update, and then what is my loss function aggregate over t steps. Hope that's clear. Standard method is called stochastic gradient or gradient descent, sometimes people say. Essentially, you look at one data. This is the ith point. You look at the observation, and you compute loss, and then you do an update. Update is by gradient, taking gradient with respect to w. And then you make a small, this is called learning rate, which is depends on how fast you go, how far you go. So those are standard method. One issue is if you look at this particular method, even like exponential gradient descent, it's another way, it doesn't get you sparse weight. So what we want to do is doing sparse weight, because if you look at this one, it doesn't set weight to 0. Yeah?
Does this loss function make sense? Because the way it's written with the indices that you have, this loss will always increase, right?
Which loss function?
The aggregated loss.
This one? Yeah, you increase, yeah.
So isn't your learner better off not learning anything then? Like, so
No, this is
you're saying that you're producing the WI from the observations 1, 2,
Right.
minus 1.
For fixed t.
let's say for a fixed t, yeah. That's probably simple to consider. For a fixed t, you want to minimize this guy. W only depends on the previous what you see. And then test on the next example. W always, if you look at Wi plus 1, it doesn't depend on Zi plus 1. Then it tests on Zi plus 1. So each time you do that. It's very standard setup in the end. Basically, you look at your update and you test on the next example, and you keep doing that. Is that clear? Or no?
But you're summing over all the next results, right?
Yeah, summing all the predictions. Predictions are unseen data. You're always summing on the.
Over examples. Or sorry, I ranges over examples. So you have t or t plus 1 training examples. And he's saying that set is fixed in advance for the easiest way to think about it.
Okay. So anyway, so the idea is get a sparse weight. So that's what I have said. And batch counterpart, there are various ways. Actually, the second part I will talk about batch in some way. But one method is L1 regularization. You put L1, it gets your sparsity. Not sparse learning. So what you can do, idea one is you just put a stochastic gradient there with L1 regularization. I think that's probably what you suggest or something. That one doesn't work because it doesn't force the weights to 0. If you look at even you have L1, whatever you have, this guy doesn't give you 0 weight. So that's a problem. We are doing some modification of that, which make it. So actually, we are very much like L1 regularization in the online setting. But then it's actually have a force of weight to 0. But then it's actually principled. The idea two is rounding small weights to 0. This is a sensible idea. The problem is there are actually two problems. One is it doesn't not quite theoretically justified, right? How do you say you don't get rid of importance weight? The other is algorithm issue. You want to keep track of non-zero weights. For some reason, when you do that, you want to when you do that, you want to make sure that you actually keep track of in a nicer way. And this one I don't want to go to detail, but it's easier to keep track of non-zero weights by using a more principled approach. So here is our approach. Our approach is very simple. It's like L1 in some sense. I will show why it's like L1. Basically, you do a stochastic gradient descent, this one. But then you on top of that, you do a truncation. You do a stochastic gradient descent, you pass to a function. Function is like shrinking that to 0. So basically, if you look at your weights, this is 0, this is your weights, you shrink that towards 0. If it doesn't pass 0, you stop there. If you pass that 0, you stop at 0. You never actually pass 0 direction. You go direction, as long as it doesn't pass that, it's the same as gradient descent. But once it passes 0, you stop at 0. So that's one. Here is the function which you go. So your weight is here. Then you try to push that towards 0. In the positive, you push down. Negative, you push up. But then you stop at 0. You never go over 0. So that's a simple fix. The claim, of course, is It's not only a heuristic, but it's solving the L1 problem. So that's the more difficult part. Basically, that's our solution. It's like L1 regularized in some sense, but it's in the online setting. Here is some assumptions we have on the loss function, which we can prove something. Basically, this kind of assumptions work for logistic regression, SVM, or other functions, but common loss functions you have, which will all satisfy. But under these assumptions, the details is not that critical. But essentially, there are some assumptions on loss function which is satisfied for all the common losses. Then you consider that. So this is a regret bound. The regret bound means this is my online performance. This compare with in retrospect, when you see all the data, any particular, the best possible W bar. You compare your performance in the prediction setting to the best one in the when you know all the data. So that's the claim is it's similar. And this is a little bit complicated to look at, but if you look at simplification, when t is large, learning rate is small, and this guy is large, then roughly this is what you'll solve. If you look at the below, it's like L1. The right-hand side is L1 regularized problem. The left-hand side is the online version of that. Basically, it's aggregate loss plus L1. So that's kind of, that's essentially, it's kind of online analogy of your L1 regularization. And in the batch setting, people know L1 will give you the sparsity. Here it's a similar situation. I will show some just examples. In the stochastic setting, basically, if you want to, many times people use online learning just to solve a batch problem. They start with a batch problem, let's say L1 regularized problem. They try to use online learning to set up, to solve that. This one essentially is a batch problem you want to solve over your training data, and you want to find W. And you can run this online algorithm like this. Basically, each time you do the update, you truncate through the 0. Once you do the stochastic upgrade, then it's forced to 0 weights. And then this one is actually fancy way of optimizing averaging. This one is not critical. This one is more of the update I talked about. And in this one is you want to use this one, go through the training data as a way to solve this problem. So that's the goal. If you do that, and you can do the similar result. Essentially, the idea is here is your, basically it's kind of solving this, this is L1 regularized problem of your data. This is R is the L1 regularized problem. And here it says your online output, once you go T steps, you have approximately to be solving the L1 regularization. So this is the solution of L1 regularization plus some small term.
I'm sorry, this was the simplification as t goes to infinity. And what happens to eta?
It's similar. So that's actually would be similar to that. It just eta goes to 0 and this guy goes to 0.
Right, eta goes to, I mean, so what bothered me about this formula is that G is the same, and of course you might have a larger threshold after you've seen more examples because you're more confident that you can push smaller weights to 0 after you've seen more examples. But
that's true. You're right. So there are issues. I think that's a good point. There are issues like that. One is you want to look at. So what is the implementation actually slightly different than that because of the issue related to what you said, and you want to tune that. But that may just make things more complicated. It's the right question to ask when you're really starting to do things. But at the conceptual level, it's like this is just conceptual level.
If your limit on eta saved you or something, that as eta goes to 0, well.
You want to do something. That's like what you're saying. That's something you want to do that. But conceptually, this is basically what you do, and at a simpler level. Then you can start to do a little bit more complicated. Those can be addressed. So this is basically this is update, and then this is the result you get. More or less, it's solved L1 regularization. So essentially, what I'm saying is this is the online counterpart of L1 regularization. So that's a claim.
Actually, we use the averaging there. What do you assume about the underlying statistics of the process?
Oh, it's just a random. If you look at here, It's actually, no, is that here? No, it's here. So the data actually is random across, just random pick I.
But you assume that you have IID or something like that, right?
No, this is the training data. You use that to solve your training.
Okay, but then the expectation is with respect to what?
With you, while online you look at one data point, right? You random sample from your data each time.
I see, all right, okay.
Right.
Gotcha.
You can actually do permutation, that's also fine. But in this particular case, it's basically essentially each each data I look at is randomly from that.
That's the only randomness here.
Right, that's only randomness, yes. It's a good question, okay. Essentially, okay, so that's the point. So this is basically, this part we just say that we try to come out with L1 counterpart in the online setting. And it's a simple algorithm to do that. Here is one way to do the least squares. That's actually, we did the experiment with least squares laws. You can do other laws, which really doesn't matter in the theory. Essentially, each time you just, you have a weight computed by using the gradient descent here, and then you shrink that towards 0. If it's larger than 0, you minus something and truncate it to 0. If it's smaller than 0, you plus something. Then you just cap that at 0. So that's the, and basically it's a simple algorithm which gives you sparse weight. And you can keep track of that. There are some more engineering details I'm not going over, but you can keep track of all these features and so on. So experiments, I just tell you some result. It's actually give you sparsity. That's all it says. There's not too much to say because we couldn't compare with other sparse online learning algorithm, right? Because there's not really any. So basically, it's UCI data. The problem of UCI data is small number of features. We really want to look large number of features. So we also add just to have an original data set, small number of feature, adding 1,000. And then there's the text categorization data. These are many data. And that particular data set, we look at Yahoo prediction data, which has also many data, many number of features and examples. Here is the graph of those data. So there are some UCI data. There are some text categorization data, and this is a Yahoo data. So if you look at basically, we are interested in achieving a lot of sparsity, and under the condition that the performance doesn't drop a lot. Performance changed by 1%. So that's what we have. It's like classification performance. You drop 1%. And due to the sparsification, usually it doesn't improve your performance. That's our observation, at least from this data. Some actually improve a little bit. But then we will see how much sparsity we can get as the proportion of original features. Here is the UCR based data. Here is adding 1,000 random feature. And for the base data, some doesn't help. Some help more. But in the context of adding 1,000 features, they help a lot. If you see that it's quite much sparser when you have only 1% drop of your precision, you can have quite a lot of drop of.
The scale is different. I mean, the point is you want to get rid of all those random useless features.
Right.
So,
right. In the large data, then there's no added random feature. They just have a large features and a large number of data. RC1, you don't see that even. Here, here you don't have this green line. You only have a red line. Here you see that has, especially on this data, which we're more interested in there. So you get a quite big boost of your sparsity.
So for the other columns where there's no green, that means that all of the 1,000 random features got positive weights?
You got some weights, yeah, got non-zero. You have
Sorry, not totally. No.
Right. Compared with basically, it's I mean, usually if you do gradient descent, there's nothing you can do. You can do some truncation or other things. Here is the question is, of course, whether you can how well your truncation do. The problem of one of truncation is it's not as principled in the sense of there's other issues with truncation. How do you keep track, as I said, and this one is actually easier to. So, but again, if you do truncation, you do also get sparsity. If you ignore that, then you have no sparsity, right? So that's what we compare to.
When you say performance is changed by at most 1% due
Yeah.
to specification,
Right.
you have also curves which show how many features are left when you increase or decrease the.
Right. There are curves. I didn't include that there. It's all yeah. So, but that's true. So that's will be nice to look at. And it's not here. But basically, roughly, it's given an idea. So it does give you basically the point here is actually it's an online algorithm. It does give you sparsity.
Does the performance sometimes improve due to sparsification?
Does that? But usually we don't see too much of that. But yes, it can happen. We do see sometimes. That's true. Okay, so here is the part one. Basically, part one just give you an algorithm, a simple algorithm. But the good thing is principled. It can be used in the scalable algorithm. That's motivation why we want to do that. And first, it's the first technique for sparse online learning. It's not necessarily the best technique. It could be better, but again, it's something there. No, so you cannot say there's no sparsity online at this point, right? There's a simple modification of SGD, so truncated SGD. It's theoretical motivated because there's a regret bound, there's online card, and essentially it shows that it's online part L1. And it works reasonably well empirically. So that's how it is. Question about the first part? If now I'm going to the second one. Second is on the batch. Okay, yeah.
So in online algorithm, normally, you incrementally add the feature, right? But here it seems you have a fixed feature set.
No, you don't. You can keep that dynamically. That's important. But that's more on the engineering side. It's possible to do that. You want to keep that dynamic. You don't want to, in the very large, you don't want to keep all the features.
Yeah, but
one reason is you don't want.
made this, you have like 10% feature net.
Oh, those examples, this has a fixed feature, right? Those is just for the purpose of illustration, just show you it actually works. But when you're really doing that, there's a dynamical version of that. This one is really just. Otherwise, I couldn't show you. I just want to show you some results. That's all. So that's good. It's not the way you're really supposed to run if you cannot store everything in feature. In that case, you do that dynamically. It's a good question.
Excuse me.
Yeah.
Can you tell me how this method compares with standard feature, like dimensionality reduction methods, like PCA or?
Oh, PCA is completely different. It's not feature selection. PCA is a dimension reduction. It's a projection to a low dimension.
Yeah, but if you are using your features as like a vector, you can then do a dimensionality reduction in that space.
Right, you can do that. And this is like L1. In that case, this one is basically it's an online counterpart of L1. L1 is one way to do that. There are other ways. I'm talking about
Sure.
in the second one. I'm talking about the other ways. So that's
what I'm trying to say is
yeah.
that the way you're getting this sparsity,
right.
Would you get equal reduction in features if you just use a simple dimensionality reduction technique? My point is, if your data has actually embedded in a lower dimension manifold, so to say, are you getting that, or are you doing something else?
No, it doesn't get. No, it's a feature selection is different than dimension reduction. Dimension reduction is in some ways more general. Feature selection is special. It's a look at the components. Dimension reduction, you don't get real sparse because then you want to say your dimension reduction itself is sparse. Each dimension reduction, each projection is a weight. That weight may not be sparse. And if you really want sparsity, you want that also be sparse. It's actually different. It's a different goal. Here, the goal is just to get your sparse weights. Dimension reduction, it doesn't mean you get sparse weights.
But if it's really in a smaller dimensional space, then most of the weights will be zero in ideal case. Right?
It could be, yeah.
That's sparse.
Yeah, in that case, it's like this.
And if it's not, then most of the weights will be. In fact, you don't get much reduction in a lot of the cases. The plot you showed looks like.
Oh, that's because they're for small feature to start with. And if you add 1,000 features, then basically we don't have other data. The point of what kind of data you want, UCI is something people are familiar with. In this case, some data you don't get sparsity. That's because they just have a small number of features. The sparsity probably maybe not the right questions. Here is, actually I have the same problem with the second part, where I just play with some of this kind of data. But if you add 1,000 extra data, you get far more sparsity here, right? So it's always get far more. So depending on how you look at it. And on some data we care about, it does give you more sparsity. Okay. Second part is again sparse learning, but it's in the batch setting. The idea is this is a more specific setting. So we want to have basically a change notation, because in this particular setting it's easier to look at a different notation. N is number of training data. Vector is for each feature. For each feature, the value of that on the different training data. So there's a basis function. Basically, each one you have a basis function, one feature function.
But, I mean, the graph you show is actually proof what Alan said. It's a property of the data instead of the property of your algorithm, right?
Oh yes, property of the data.
You do not get the sparsity.
Oh sure, that's always the case. For a lot of data, you don't. But
The amount of sparsification you get depends on the beta that you choose, right?
beyond data, the data depends on data.
Yeah, no, but it depends on the
G
degree to
also.
which you do truncation, and you chose that degree so that you
Yes.
wouldn't get much reduction in performance, and so of course that.
Right, exactly. So this is a part, right? If you,
Some
I
data
can always
has
choose,
reductions.
I can always get a very sparse, but it's a very low performance. So that's why we set this one threshold to do that. And in that case, depends on data. Some data is much easier to get sparse. Some data it doesn't. So that's always the case. But you know, this is not surprising. There's no algorithm which works on all data. We all know that. So it's just you try to do something, right? The second part is it's a similar problem, different notation. This is called basis function. Each basis function basically is a feature stream. If you think about NLP, you generate the feature stream for different data, and it's different features will have data can have across n is number of samples. So you have a D basis function, you have D features, and you observe something Y. And here I'm most talking about regression setting. In the previous you can get other settings, but here is you have again you want to have a W is your weight vector, which is D dimension. D dimension is actually is your feature space, and the linear prediction function. Basically, it's a combination of your W vector and your feature, which gives you the function, and you want to pass through the least squares loss. So you want to minimize the least squares loss, empirical loss of your linear function here, and there's risk. Risk is like this. So least square problem is really like that. Okay, so that's the setup. And it's kind of opposed in the sense of I want to interest in the number of features, a much larger number of dimensions. So that's actually the problem in natural language. A lot of real applications nowadays, large-scale data, could happen. Many more features than the number of examples. So in that case, if you just solve that problem, it's not well posed, but you can have a constraint. The particular constraint that I'm looking at is there's only a few relevant features. There are many irrelevant features, but only a few relevant features, which means the sparsity. You want to have target function is the exact or approximate sparse. So one learning method which actually, in theory, works well under assumptions will be the subset selection. Subset selection basically is you look at the features, you look at all the weight function which has a zero norm, means the number of non-zeros, small number of non-zeros, and you try all the subset of these features, and you say who has the smallest loss function. The problem of that is basically this is essentially the most fundamental feature selection algorithm. If you can do subset selection, you're more or less looking at the feature selection. The problem is a combinatorial problem. It's very difficult because you have many different combinations which can have exponential time. So this talk is really about how good one can solve subset selection using greedy algorithm, this part. So linear prediction is what we are interested in. And the statistical model is when I start with a target function. My observation here is a target function. This is a target weight vector plus some noise. Noise assumed to be zero mean and have some noise level sigma variance. And the assumption is this guy is sparse. It has either only small set of non-zero components. This small set is much smaller than n, and which n is much smaller than your number of total features. Or it can be approximated by such a vector. It doesn't have to be exactly, it could be approximate. The learning method which work well in this certain conditions would be, for feature selection, would be subset selection. Statistically, which means this gives a good estimate. The problem is inefficient, this method. So we want to look at, there are a couple of solutions to that. One is which covered in the first part of the talk, convex relaxation using L1 regularization. You put a L1 regularization, which give you sparsity of your weights. So that's a common method. It's very widely used nowadays. And the other is simple greedy method, like forward greedy, forward feature selection. Basically, each time you add one example at a time, or one feature at a time. Another name of that is boosting. Boosting essentially is a forward feature selection. The other is backward feature selection. You do that backwards instead of forward. And I'll give more details. Under some assumptions, this can approximately solve this feature selection problem. So that's a conclusion people study in theory, and this theory come out very recently. Like people might heard of something like compressed sensing, which essentially is basically looking at this. Compressed sensing is a noise-free version of what I'm talking about, and basically all they are doing is just performance of these algorithms. Okay.
Sorry, what's the term you just used?
Compressed sensing. Have you heard of this term?
Sensing, okay.
Compressed sensing is quite been popularized recently. About there are some applications as well. It's essentially one application they always talk about is you try to reconstruct image from multiple cameras. You randomly look at the multiple cameras.
Yep.
You look at the image, and then you combine that. Then you get a better image. Something. Essentially, you have a signal, sparse signal, and you project that to random direction. And also in the streaming application, they also look at that. For example, another example is, let's say Walmart has a lot of items, and you want to keep track of the top 10. For example, top 10 items of Walmart every month, right? You want to, but you cannot store all the items. If you cannot store all the items in your streaming algorithm, what you do is you random project. Random project that, let's say you have, 10 to the 9th items. You random project to, say, 10 to the 4th, which then you can manage. Then you keep count on that, those random projected, you can do that. And then you can have one algorithm to reconstruct your, the top 10. That's sparsity. Top 10 is you have a decay of items being sold. So there are applications of that, various applications which people are interested in, but that's a special case of sparsity. This can be applied to that. But this also applies to NLP in the sense if you really care about a small number of features, this is feature selection. The particular algorithm I'm going to talk about is forward-backward feature selection, greedy algorithm, in a way that you can actually prove something. It's actually try to solve the subset selection better than either forward or backward. It's by combination, and you can show some performance of that. Some assumptions really is about noise assumption. It's noise have sigma level. Basis are normalized, which is not critical, just more convenient. And actually one critical condition, usually when you see this literature or analyze this algorithm, is that the sparse eigenvalue condition. Basically, if you have d basis functions and this number is larger than number of samples, these are degenerate. They cannot be linear independent. However, you can ask whether a small subset, k, for example, k is much smaller than n, whether they are linear independent. The case is a lot of, in some example, if you can say that for k, k is much smaller than d and is much smaller than n, which is linear independent. In this particular case, which means that eigenvalue of this system. If you look at this matrix of f, every k matrix, every k-basis functions, you look at the covariance matrix, it's the eigenvalue of that is larger than 0, which means it's uniformly independent. Under such assumptions, you can try to come up with algorithm which actually recover the set. And here is upper bound of eigenvalue, which is less important. Rho is more important. Basically, rho really means whether a small subset of F is linear independent. It's one characterization of that. Under it's not linear independent. Under this linear independent assumption, then you can actually prove something. So this one is the L1 regularization. I'll just briefly say what people do. Essentially, we start with L0 regularization, which is subset selection. L1 is the smallest convex relaxation of this problem. This one is not convex. This one is convex. Therefore, people look at this problem as a substitute for solving a hard non-convex problem. Theoretical analysis exists and very recent works. There are some also in process and there are some exist. But the problem of L1 is very difficult to control sparsity. If you really want to highly sparse, it's actually suboptimal. So when I actually show you result online, it's really like L1. In fact, if you really don't care about scalability, you want to try to do that like what down here, it could do better than L1. So algorithm talked about here, in the batch setting is better than L1. So it can lose statistical performance. And the second thing is it's hard to control the sparsity. It's not explicitly controlled. It's only controlled by adjust L1 in some sense. So here is the algorithm, forward greedy algorithm. That's a different algorithm than L1, which is essentially each time you look at one weight factor, then you add one component greedily. Basically, you add one component from one feature, such that that feature, that component will greedily reduce your cost function. So that's greedy algorithm. There's a problem with that, considering feature selection. Is assume, let's for example, your target, just say noise-free case. Your target here is a combination of two basis functions, f1 and f2, but f3 is closer to y than f1, f2. Then what you do is first you look at f3. That's your select, because that's closest to y. It's give you the largest error reduction. Then you're starting to do with f1, f2. At that point, you already made a mistake, because at this point, this guy shouldn't be here once you see f1, f2, but the greedy algorithm forward only does not correct that. Therefore, you don't achieve the highest sparsity. You get something which is not necessarily the best solution. You have three basis functions. These are two basis functions to represent your function. The correction to that, people look at is backward greedy. So they start with the full model. There's actually a lot of maximum entropy, I think, in the NLP has tried to do the backward instead of forward. You start with a full model, and then each time you eliminate one particular weight. You look at the full model, and each time you're starting to remove one weight at a time, and so on. You just going away with that. This problem is, first, it's computation expensive because you start with full model. Secondly, it have an issue of it can overfit the data. Because if you have a lot of features, you start with something that's a complete overfit the data. It could happen. If that happens, you cannot differentiate bad feature from good features. You could basically, you remove any feature, it gives you some have no improvement or very small improvement. But that's simply because you overfit the data. So the problem is if you look at the theory, it only works when n much larger than d. In that case, you don't overfit. When n is much smaller, the number of samples is much smaller than the number of dimensions you overfit, you cannot directly use backward greedy unless you already start with some regularization to start with. Basically, you have to start with something which doesn't completely overfit your data. Then you perform that backward greedy. And the behavior can be simply. So what we talk about is a combination of these two ideas which solve the both. if you look at the pro and the cons of forward greedy, first, computation efficient. It doesn't overfit because each time it's sparse. Second, but the problem really is the error doesn't get corrected. Backward greedy can correct errors because you remove, you look at the full model, you remove anything. But there's a condition on that. If you can achieve that only when you start with something which is not overfitting. So the combination is simultaneous doing forward and backward greedy algorithm. And first, computation is more efficient because you always keep a sparse model instead of a full model. It doesn't overfit because it's sparsity again. Then you also have the advantage of backward greedy in the sense error made in earlier stage can be corrected using the backward step. So I think the main issue here is how do you take a backward step, as well as how do you want to say it's actually effective. So that's the most question I try to address here. This is the algorithm at the high level. How do you take a backward step, and I will give a result to say it's actually effective. So basically, you keep track of each time you keep an index, okay, and you keep track of forward step, squared error reduction in the least squares loss case. In the other loss case, you can do using other loss reduction. Basically, how much reduction you get by using a forward step, the cost. In the backward step, you decide whether you want to make a backward step. It's done adaptively to say, at each k, you look at the reduction of forward step. If my backward step error increase smaller than half of that, then I will try to do a backward step. Otherwise, I don't do that. The reason for doing that is because I don't want to remove any progress made in the forward step. If I only remove half of the progress, I'm okay because I'm one forward and backward step. I'm still actually making at least half the progress of the forward step. So that's the idea. And here is a more pseudocode. This one is a huge pseudocode of that idea. Basically, you do that. The key is you try adaptively doing the backward step by computing half of forward step. And because of it doesn't remove the forward step, and actually there's a stopping criteria. And stopping criteria is once forward step goes to smaller than epsilon, you stop it. In that case, you can show that given the stopping criteria, the forward each forward step at least will contribute epsilon over 2, because it has to make a decrease of at least epsilon. The backward can only remove half of that. Therefore, you start with R0, you decrease the error. This is the number of forward iterations you can run until you stop. So it's actually, it will terminate. In this example, you can look at that. So it helps because, again, you look at F3, then you look at F3, F1, F2. So, but after you look at F1, F2, removing F3 doesn't increase your cost anymore. Therefore, you can actually remove F3 because you already see that Y is only represented by F1, F2. Therefore, you can remove that. So it actually fixes the problem using this example. And there are theorems about what you can do. The theorem basically says under certain conditions, this is kind of eigenvalue conditions. And this is like noise conditions, and this is weights not too small, separated from noise. Then you can show that when the algorithm terminates, we can find the exact set. When the noise actually, when the weight vector is not too small. If weight vector is close to noise, you cannot distinguish that from noise. Otherwise, you can distinguish. So this is, with a sparse target, the noise vector is doesn't distinguish from noise. And then you can show that you can estimate the parameter. This is the part where compressed sensing people would be more interested in rather than the feature selection, because they want to see when you project to smaller dimension, reconstruct your weights is close to the true weights. This is the true weights. This is the weight you would reconstruct it, and those bounds would be useful. And also the algorithm terminates in certain iterations. I probably don't want to go over how do you prove that. And there is a generalization of that approximate target instead of an exactly sparse target. In the approximate target, there are some weights which can be smaller than the noise level. In that case, you cannot identify those weights, but you can at least identify the weight is larger than noise level. You look at with the number of weights which is smaller than noise level, you can show the feature selection quality is is the number of weights which is actually larger than the noise level, and plus your approximation error. And basically, this gives you some results about how well you do when you don't have an exact sparse and your weights are not that. So here is some try to compare. One reason we look at the artificial data is because we know the choose. And this is a forward greedy. This is L1 regularization, which both are very common method in this. And this is a forward backward greedy. In the artificial example, we know the ground truth, therefore we can compute the training error. The idea is the forward backward greedy is trying to minimize this training error at the same sparsity level. Basically, sparsity is 5. Truth is 5, and when I reproduce, I use 5, the largest coefficients. And here is L1, it doesn't do very well. Forward is actually better than L1 regularization. And so always here is better because the training error is much smaller with the same sparsity level, and the parameter estimation, because I know the ground truth parameter estimation is always smaller. Feature selection error means the set, whether you choose the right set. There's five features, and the average is 0.2 incorrect features choose, and the others you can have a much larger. So that's on the real data. We just play around again with UCI because I didn't add random noise features at this time. Basically, it's to look at the Boston housing because that's a regression problem. I'm talking about regression here. Forward greedy give you steps. This is the first feature is select, second feature, fourth feature, fifth feature, and so on. You give a set of paths. The path is the number of features it selects. Forward backward sometimes can remove features. You look at the features, this is kind of feature is select, and you're starting to remove at one point, and so on. And L1 is similar to that. I don't know if people heard of this thing called the LARS, path following. I'm not sure if people are familiar with, some maybe heard of that. So this is LARS output. Essentially, there is a way to interpret as a kind of similar to greedy, but they have, and they path following, and it gives you a path of which feature is added, and it can also remove features.
So sorry, does path following start with, is the idea that you start with very strong regularization and you gradually relax?
Right, exactly. But it gives you a whole path, therefore it will give you all these intermediate features.
Sure, yeah.
Right.
So this is, for people in the audience who think about things like deterministic annealing, this is quite similar to that.
Right. Yeah, it has one specific algorithm to do that. So they basically compute the exact where the switching points of
the phase shift, the phase transitions.
Not a phase. Basically, essentially, if you think about annealing start from a very high regularization condition, when the decrease starting to decrease, the feature doesn't change, right?
Sure, but there's some.
At one point, the feature started to switch,
sure.
Right? And then these are all those points, right?
Sure.
Features starting to change, and then you just keep track of that. This is very recent, maybe 2004, but then there's a lot of interest in the machine learning community. There are a lot of path following algorithms.
Whose paper is it?
They started with Stanford, like it's Efron and Tiprani and Hasty, those people.
Yeah, okay.
But then right now there are many more papers on this particular topic. The difference actually, if you look at this, they're similar in the sense they can add feature, remove features. The difference is that this always by keeping track of feature by using how large your L1 regularization is by doing that. Here it doesn't. It always keeps track of original objective function. Only thing is sparsity. There's no added penalty. So you have a smaller bias. It actually turns out to be a good thing if you really want to just reduce your, given any sparsity, reduce how much you get. And we can look at this. This is the training data. The training data, again, is a look at here. L1 is here. L1 in the very sparse case is actually the second is already getting the wrong feature. The reason is you have a lot of bias because you have a high L1 regularization parameter, which doesn't means basically you are modifying your objective function. not a least squares error, but it's penalized, and there's a large penalization, so give you a wrong feature, and eventually it fall down.
Sorry, the x-axis is labeled sparsity. Do you actually
Right,
have
it is
density, number of features?
This is the number of features.
Number of features, yeah.
This is the number of features, the number of bases you like. So you look at the path. Basically, how you determine is you look at the path. In the forward, you just the first few, right? In this guy, you can remove. Then you actually always, in this particular, so because the algorithm is strong, you always look at the last one, which gives you the, let's say, particular k. K is number of sparsity. You look at the last time it has a k. But basically, that is the k which gives you the smallest training error. Because the way it's always the last. Similar here, it's actually very similar. If you look at here, the last one is the smallest regularization. You have a smaller. So it's also the smallest training error if you remove the regularization, the square error, given any sparsity. So basically, you just look at this path, the last one, you get your k. So then you plot.
What kind of data set is this?
This is Boston housing. So there's just one. Oh, do you know? Oh, you're not familiar. Oh, this is a regression problem. Basically, it has it's a housing data for the area code in the Boston area in certain year. I don't remember. And then they have data like that. You want to predict the price of the, and they have different features like number of rooms, where it's the crime ratio, and so on. So it's a small data. Again, a lot of UCI data is small, so that's the issue. Basically, probably I should add 1,000 features like the other case.
Well, all these methods are fairly expensive, right? Because at every step, you're iterating over all the possible,
Right.
all the features in your set, deciding
Yes.
whether to put in the ones that are out or take out the ones that are in.
That's true. So you can argue it's expensive. Depends on how you argue, but it's much better than subset selection, which you choose every possible thing, right?
Sure.
This one at least is achievable.
So actually, I was going to save this question for later, but since it follows on.
Yeah.
As long as you're doing that computation, an obvious thing to try also would be simulated annealing. Since you know the benefit of each of the possible moves, instead of greedily choosing an insertion or deletion move, you could choose one at random.
That could be, right. It's not included here for two reasons. One thing is you want to prove the effective. One reason this is theoretical, in the sense I want to give an algorithm which is provable. The other reason is that it's based on implementation. How do you implement that? That's our issue. It's not a standard algorithm. Let's put it that way. It's not standard sparsity. When you talk about to the machine learning people, first they will think about the L1 regularization. Then we'll think about boosting type of thing. So the two I'm comparing with the standard. When you talk about simulated annealing, it's not the standard.
Well, the point about using simulated annealing is to find something which optimizes an objective criterion, which is a regularized error on the training set.
It could, yeah.
So you have some penalty for too many features, but you also have a benefit to modeling the training data when you have a lot of features. And so you can't try all subsets, but you can just use simulated annealing to optimize that objective function.
Sure.
So you're not going
approximate. You cannot really optimize.
Sure.
Right. But that's true. So that's why it's possible. It could even do better than this. I don't know. But then there's no statement. One part of this is that there's some statement, and also it's very direct modification of the forward. So, and it's very similar in the sense of path following in the L1. If you look at the path.
Ordinarily with simulated annealing, I imagine that as the temperature goes to zero, you end up at your algorithm anyway. So you may
it
still
could be.
able to
That might be. I don't know. I mean, that's a possibility. I agree. So it's a possibility. But I haven't done with that. Yeah. Well, test is a different story. The reason is if you look at truly sparse data, because the first two, based on this data, L1 doesn't do well, right? Simply because if two cases, two features, and L1 doesn't do well on the training data, it doesn't do on the test data. You don't overfit. But then, if you look at the training data, at least on this data, assumable actually here is a big change of training error, but somehow doesn't show in the test error. Therefore, basically says sparsity doesn't. Probably there's only two relevant features, maybe. It doesn't really show up. So this algorithm, although it do very aggressive on training data in the term of sparsity, it doesn't really do well on the test data. But that point is just say sparsity in not always help, basically. But I just want to give still it does give you the, on the training data, it does what it's supposed to do, basically. Any sparsity give you a better training out. That's the only thing it can control. It doesn't control the test error.
The second graph that you showed isn't the fault of your algorithm.
It's not the fault of my
It's the
algorithm.
fault of the criterion you're optimizing. Is, you know,
Right.
on this particular data set, it didn't work.
Exactly. So it's not for my. But I just want to show that it's not always that directly, because when you talk about machine learning, sometimes you want to ask the test data, right? It's not the fault of the algorithm. It's not the right criterion for this particular data. But at least in the extreme sparse case, you still can. In this case, both forward and forward backward get it right, but L1 it doesn't do as well. Okay. Essentially, what we learn from the experiments is one thing is exactly what you said is. First, it does the right thing, achieve the design goal. That's all it says. On the real data, not necessarily best measure of complexity, because test error, small complexity in terms of sparsity doesn't necessarily the test error, basically. Not always, basically when you say feature selection, you can always do that. It does not necessarily say it always gets you the best test performance. That's all it says. So the summary of that is subset selection is difficult. This one is people use approximation. L1 forward, and here is a different ways, and you can have a performance. I'm not sure compared with similar to linear, but compared with this one, the performance bound you can get is stronger, and also intuitively you can see that example is also good, as well as on practice. If you just look at the design goal, it does achieve that. So it's closer to subset selection. It's not necessarily solve that in the Boston housing example, but at least it's closer to subset than anything else. So it's achieved that goal. Okay, so that's I'm done.
More questions?
Yeah.
I forget the setup. Is there any kind of condition on these basis functions, as in boosting, to have a certain accuracy? Or?
It's a different type of condition. Yeah, no, it doesn't have that type of condition. I know the condition you talk about. The condition here is the linear independence of your basis for small set of linear basis function.
Well, the true basis.
The reason for that is if you think about feature selection, if a small set of features are linear dependent, then you cannot do feature selection, right? Because they have a different representation, which give you the same result.
Right.
So that's why it shows up there at the most intuitive level. Now you have to say it's reasonably further from that degenerate condition to talk about feature selection. But it's a different type of condition. Boosting doesn't have this particular condition. They have a different set of conditions. They actually look at a different setup than this particular.
Yeah.
Right.
Questions? Good.
Okay.
Well, let's thank Tong again. Thank you very much for.
Sure. Thank you.